So today's lesson we are going over the derivative of natural exponential functions. Natural means e to the power of x. If you remember, e is Euler's number, which is approximately 2.718. And we can actually use this function here, or this expression. And if we look at this expression, if we plug in n equals 1, we get 1 plus 1 over 1, which is 2 to the power of 1, which is 2. Oh, I got my laser on there. There we go. 2. If we plug in n equals 5, we get 2.48832. If you plug in 10, 2.59374. You can see what number we're sort of getting closer to. N equals 102.704. So much closer. 813.829. So this expression, if you take the limit of this expression as the n approaches infinity, that's Euler's number. Now there are other ways to calculate it. I don't know which one you've learned previously, but there's also the 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on and so on and so on. But this is what we're going to be looking at today, the natural logarithm. So Euler's number to the power of x. Now we also have the natural exponential. We also have the natural logarithm, or ln, but we will look at that in another lesson. Okay, so basically we want to figure out what's the derivative of a natural exponential. So what I'm going to do is, using Desmos, we're going to graph two things. One, e to the power of b times x, and that was a bit of a mistake there. We're also going to graph the derivative of e to the power of c times x. And then we're going to compare them when both b and c are 0.5, 1, and 2. So I already have that here. So here is e to the power of b to the x, where b is 1. Okay, and if I turn on the other one, you can see when b and c are both 1, they are identical. Well, what about when they're both 1.5? Not quite identical, but notice that if you have an exponential function, like just e to the x always goes through the point 0, 1, because anything to the power of 0 is 1. This one intercepts the y-axis at 1.5. That's interesting, since we made the exponent c 1.5. Well, what if we did 2? Same thing. It looks like their exponential growth is the same, right? Because one's not growing faster than the other. So that's an interesting point to make. And also, it's now going through 2. The y-intercept of 2 when I make the coefficient 2. Well, what about when I make it 0.5? Change that so we can go down to 0.5. I'll do the same thing here. Again, it looks like their exponential growth is growing at the same rate, but the y-intercept is now 0.5. So what does this tell us? This tells us that the derivative of e to the x is e to the x. And that's fascinating in and of itself. But if you had something else, like the derivative of e to some function g to the x, like 2x, well then the derivative is still, it's the exact same, e to that 2x, but then you multiply it by the derivative of that function, which is why we were getting those different y-intercepts. Right? If you had e to the 2x, the derivative would be 2 times e to the 2x. And that 2 coefficient out in front changed our y-intercept to the value of 2. So let's try a problem with this. Here we have e to the 3x. Well, to figure that out, the derivative is then just going to be the exact same thing, e to the 3x. But then we're going to multiply that by the derivative of 3x, which is 3. So we get 3e to the 3x. That was a terrible 3. 3x. There we go. The derivative of e to the x being e to the x itself, you might have guessed that the case if when you did table of values, when you did exponential functions, right? When you found first differences, the first differences were the same as the second differences. And if you decided to keep going, they would be the same as the third and fourth and fifth and so on and so on. And remember, finding first or second differences finds the rate of change of something. Finding the derivative finds the rate of change of something. So the fact that all those first, second, and third differences were the same would tell you the same thing with the first and second and third derivatives. If you just have e to the x, the first derivative would be e to the x, the second derivative would be e to the x, and so on and so on and so on. So let's try some examples then. Here's our first example. We'll do part A. I'm going to do it over here so I have lots of room. Although it doesn't require lots of room. So we have d to x equals e to the power of x squared minus x. So what is the derivative of that? So the derivative then would be just that exponential function, e to the x squared minus x. But then we need to multiply it by the derivative of that exponent here, which would be 2x minus 1. There you go. One step. There's your derivative. Now let's try part B. Now part B, to find the derivative of f at x, so f prime at x, we have two functions with x here. Right? We have an x squared, and then we're multiplying by e to the x. So that's a product rule question. So first we can find the derivative of x squared, which is 2x. And then we'll times that by e to the x. Now we're going to add, we're going to leave that first part, x squared, and we're going to multiply it by the derivative of e to the x, which is e to the x. There you go. That's it. If you like, you can factor out an e to the x. So we have e to the x times 2x plus x squared. So our second problem says, given f at x equals 3e to the x squared, determine f prime at -1. So let's first determine what that first derivative is, f prime at x. So the derivative is just going to be 3 times e to the x squared. And then we have to multiply it by the derivative of this exponent x squared. So the derivative of x squared is 2x. So we can simplify that a little bit, so that gives us 6x e to the x squared. Now if we want to figure out what that is at 1, we're just going to substitute -1 in for x. So we have 6 times -1 times e to the -1 squared, which would be positive 1. Okay, so there we go. We have -6e. So our last question says, determine the equation of the line of the tangent, which is a line, of the following where x equals 2. Alright, so to find the equation of a line, you need to know a coordinate on that line. So if x is 2, we can sub in 2 into this equation to figure out that the y coordinate would be, so we'd have e squared divided by 2 squared, which is 4. So we would have e squared over 4. So there's the y coordinate. Then we also need to know the slope at that point at 2. So to find the slope, we're going to first find the derivative. So dy by dx. And this looks like we could use the quotient rule for this one. So for the quotient rule, first we'll have the derivative of the numerator. So derivative of e to the x is e to the x. And then multiply by the denominator, which is x squared. Then subtract the derivative of the denominator. So the derivative of x squared is 2x. And then multiply by the numerator, which is e to the x. And then divide all of that by the denominator squared. So x to the 4. Right? X squared would be x to the 4. Now we can simplify that a little bit. So we have an x in every term. So we can get rid of 1 there and 1 there and 1 there. And then we can also factor out an e to the x. So we get e to the x times x minus 2 all over x cubed. So we want to figure out what this derivative is when x is 2. So we're going to substitute 2 in there, but you can see right away when we do that, this bracket here is going to be 2 minus 2, which is 0. The denominator is not 0, but the numerator will be 0. So this is going to equal 0. What does it mean when the derivative equals 0? It means we have a horizontal tangent. So we have a horizontal tangent at the y-coordinate e squared over 4. So that's our line. Right? Y equals e squared over 4, which is approximately 1.847.